From complex stroke mechanisms to the simplicity of arithmetic part 1 number 1572, March 13, 2026, Gerald C. EclaireMD Foundation, category, Mathematical Simplicity and Medical Sophistication. Introduction. My purpose in developing the TSI models is practical rather than theoretical. After suffering a hemorrhagic stroke on June 21, 2025, my main objective became preventing a second stroke. To accomplish this, I began monitoring my pathophysiological data daily and analyzing them through mathematical models implemented in a customized medical AI system, Chronic, on my iPhone. Every time I enter 3 new biomarker values, glucose, SBP, and into my iPhone, my medical AI system immediately calculates several additional indicators. These include extended blood pressure variables such as pulse pressure PP, mean arterial pressure MAP, SBP spike, and 3 stroke risk indicators called the Stroke Risks Triggering Sensitivity Index C. One of them, TSI-2, uses only PP and SBP. The other 2, TSI-3A and TSI-3B, use PP, SBP, and daily average glucose EEG. If these TSI values remain within the safe range, for example, below 100, I know that my vascular system is operating within a controllable range for that day. If my TSI values rise above 100 during the day, I immediately take corrective actions. These corrections include reducing carbohydrates and sugar in my meals, doing post-meal walking, practicing breathing exercises, inhaling for 4 seconds and exhaling for 8 seconds. Repeat it 4 to 5 times, and avoiding emotional or stressful conversations and thoughts. Each day I measure my glucose about 96 times and my blood pressure about 20 times, collecting hundreds of data points. By continuously monitoring these signals and receiving immediate feedback about my vascular pressure and metabolic condition, I hope this dynamic system will help protect me from having another stroke. Scope of this article. This article explains 4 scientific ideas derived from my recent research work. 1. The difference between my 2 developed models, TSI-2 and TSI-3B. 2. I use Isaac Newton's equation F equals m asterisk a not F equals m plus a to explain why the mathematical operation of multiplication represents real-life interactions. Isaac Newton observed about 400 years ago that multiplication better describes nonlinear and interacting variables, while simple addition represents linear systems. Most biomedical phenomena are nonlinear and dynamic, therefore, simple linear explanations are often insufficient to describe complex real-life pathophysiological situations. 3. The difference between math and physics-based mechanistic scientific modeling and the typical statistical approaches commonly used in medical research. 4. The use of viscoplastic energy modeling and calculus to describe the behavior of complex biomedical systems. This discussion focuses strictly on scientific reasoning and measurable facts. I have no intention of praising or criticizing any branch of science. The discussion is based purely on scientific principles. Section 1. Comparison between TSI-2 and TSI-3B. TSI model was designed to quantify the triggering sensitivity of stroke risk using measurable pathogen physiological variables. The TSI-2 model is defined as TSI-2 equals SBP dBP over 45 asterisk SBP 120 asterisk 100, where SBP equals systolic blood pressure, dBP equals diastolic blood pressure, PP equals SBP dBP pulse pressure indicating vascular stiffness. This model contains 2 mechanical factors. First, pulse pressure reflects arterial stiffness. When arteries become stiff due to aging or vascular damage from obesity, changes occurring over hours or days, and diabetic glucose exposure, changes occurring over minutes, pulse pressure increases. Second, systolic blood pressure represents the acute mechanical load acting on the vessel wall. It can change within seconds. Therefore, TSI-2 represents purely vascular mechanics. TSI-2 equals arterial stiffness PP 45 multiplied by pressure load SBP 120. However, stroke risk is not determined by blood pressure alone. Long-term metabolic damage from diabetes has severely weakened my vascular system. For example, my cerebral microvascular calcification was mainly caused by my uncontrolled type 2 diabetes (T2D) during 1990 to 2009, when I relied only on diabetes medication without making lifestyle changes. According to my viscoplastic energy analysis, this period contributed approximately 91% of my total stroke energy. In contrast, the following 16 years 2010-2005, when my T2D was well controlled through lifestyle management without medications, contributed only about 9% of my stroke energy. To incorporate that factor, the TSI-3 model adds glucose exposure, TSI-3 equals SBP dBP over 45 SBP 120 CGM 140 120, where CGM equals estimated average glucose measured through a CGM device. In this formulation, stroke triggering sensitivity becomes arterial stiffness multiplied by systolic pressure load multiplied by glucose metabolic damage. The difference between the two models becomes clear when examining real-life data. The most important point is that I chose multiplication to represent nonlinear and dynamic interactions, similar to Newton's physical laws. Where interacting variables are multiplied rather than added, addition is more suitable for linear and static situations. After my stroke in June 2025, my blood pressure control improved significantly. As a result, the TSI- curve declined. However, my daily average glucose level increased by approximately 10% after the stroke because the stroke disturbed my metabolic balance and reduced my daily physical activity. Since TSI-3B multiplies the blood pressure factors by the glucose factor, the TSI-3B values did not decrease as much as TSI-2, as shown in the attached figure. In other words, TSI-2 reflects the reduction in post-stroke TSI resulting from my improved blood pressure. Contrast: TSI-3B shows a smaller improvement because of the metabolic burden from higher glucose after my stroke. This difference is important. C-2 tells me how well my blood pressure mechanics are controlled. TSI-3B reminds me that glucose control remains critical. This feedback forces continuous attention to metabolic condition in addition to blood pressure. Section 2, Isaac Newton's equation, and the power of multiplication. A fundamental scientific principle explains why the TSI model uses multiplication rather than addition. 400 years ago, Isaac Newton formulated the law of motion, F equals m asterisk. Force equals mass multiplied by acceleration. Newton did not write F equals m plus a because that would be physically meaningless. Force comes from the interaction between mass and acceleration. If either mass or acceleration becomes larger, the resulting force becomes larger. If both increase at the same time, the force increases even more. This equation illustrates a key property of real-world systems. 1. Interacting variables produce nonlinear dynamic behavior. 2. Multiplication captures interaction. 3. Addition assumes independence and produces linear static behavior. For example, 2 plus 3 equals 5 but 2x3 equals 6 when three factors interact. 2x 3x 4 equals to 4 but 2 plus 3 plus 4 equals 9. This amplification reflects how most real-life systems behave. The vascular system is no exception. Stroke risk does not arise from blood pressure alone or glucose alone. It arises from their interaction. 1. Stiff arteries increase vulnerability to high blood pressure increases mechanical load. 3. High glucose damages vascular structure. When these three factors occur together, the combined effect becomes larger than their simple sum. That is why the TSI model used multiplication. This is part 1.